Hey everyone, and welcome to This Explainer. I am absolutely stoked to have you here today. Our mathematical focus right now comes straight from section 11.4, and it is all about decoding distance-time travel graphs. We're not just going to sit here and stare at boring grids and numbers today. Instead, we're going to learn exactly how to turn that raw data into a vivid, unfolding story. So lock in your focus, and let's get right into it.
Think about this for a second. Can a simple line graph actually tell the complete story of a 200-kilometer race? Usually when we look at math problems, we just see these abstract lines on a page. But if you know how to speak the language of the graph, those lines literally transform into a real-time physical journey. Today we're going to track two travelers, Karen and George, and we're going to let the graph reveal exactly who did what, when they pulled over to rest, and ultimately who won.
Okay, let's dive into this. Think of our arena as the 200-kilometer stretch between two towns, Springton and Watworth. Now, on our vertical y-axis, we're tracking the actual distance traveled, starting from absolute zero all the way up to our destination at 200 kilometers. And on the horizontal x-axis, well, that's our clock. It's tracking the time of day, kicking off at 0900 hours in the morning and running straight through the afternoon to 1400 hours. This grid? It's basically the stage where our whole story is going to play out. To make sure we've got this totally locked down, here is our roadmap for today. First, we'll cover the distance-time graph basics. Then, we're tracking Karen's journey. After that, plotting George's route. And finally, we'll calculate the final arrival time.
All right, section 1, the distance-time graph, building the foundation. So our very first rule is the sloped line. Basically, anytime you see a diagonal line going up, it means there's active movement happening over time. But the really crucial detail here, the steepness dictates the speed. It's super simple. A steeper incline means a much faster pace, while a gentler slope means they're taking it a bit slower.
On the flip side, we have the horizontal line. So the crucial point is, a flat line does not mean the journey is totally over. It just means time is ticking forward, but the distance isn't changing at all. Our traveler has just paused. Zero distance covered over time simply equals a stop. Makes sense, right?
Moving right along to section 2, tracking Karen's journey, a variable pace.
Just take a look at the overall shape of Karen's route mapped out for us. It is definitely not a straight, simple path, is it? It's kind of a jagged line, with changing slopes and these noticeable flat sections. This immediately tells us, even before we touch a calculator, that Karen's journey is highly dynamic. Her pace is all over the place, and she's clearly making some pit stops along the way.
Let's actually break down her trip by reading those axes. If we trace her line back to where it starts, down at distance 0 on the bottom left, we can see she departs Springton exactly at 0900. Now, as she drives, notice those two perfectly horizontal sections on her line. Like we just talked about, these are two distinct stops. Time is passing, but she's covering zero new distance. So after this mixed bag of driving, stopping, and driving again, we follow the very end of her line to the top right. Bam! She hits the 200-kilometer mark at exactly 1400, meaning her total journey took her 5 hours.
Let's move to and see how this builds in section 3, plotting George's route, the steady challenger.
Now, let's contrast Karen's rather leisurely trip with the raw data we have for George. Karen gave herself a nice head start at 9 a.m., but, she took multiple breaks. George, on the other hand, he starts a whole hour later at 10 a.m., but the data tells us he travels at a constant, unwavering speed of 80 kilometers per hour, and he does this without stopping even once. What does that mean for us? It means George's line isn't going to be jagged at all. It's going to be one continuous, perfectly straight, diagonal line from the absolute start all the way to the finish.
To actually plot George's line, we need to figure out exactly when he crosses the finish line. Let's just walk through the math step by step together. We know his start time is 10 o'clock. We know the total distance to Watworth is 200 kilometers, and we know his steady speed is 80 kilometers per hour. To find his travel time, we just use that classic formula. Time equals distance divided by speed. So 200 divided by 80, that gives us 2.5, which means George's nonstop drive takes exactly 2.5 hours. Finally, we just add that 2 hours and 30 minutes to his 10 o'clock start time, locking in his precise arrival time at 12:30.
Which brings us to the big finale. Section 4, the final arrival time. Who arrived first?
Now, what's really interesting about this slide is how we actually visualize the final outcome on the grid. I want you to mentally plot George's arrival for a second.
He starts at 10 on the bottom axis and shoots a straight, relentless line up to the 200-kilometer mark, landing right at 12:30. Meanwhile, Karen's jagged line, even though she started an entire hour earlier, doesn't hit that top 200-kilometer ceiling until 1400. The visual gap between George's finish and Karen's finish on that top axis, that is the exact answer we've been looking for.
So let's do the final dramatic subtraction. Karen arrived at 1400. George rolled in at 12:30. The difference between those two times is exactly 1.5 hours. Think about that for a second. Despite giving Karen a full 1 hour head start, George's relentless, constant pace of 80 kilometers per hour meant he arrived exactly 1.5 hours, or 1 hour and 30 minutes, earlier than Karen. He literally came from behind to take the win.
And this brilliantly illustrates exactly why understanding these core concepts is just so rewarding. By simply grasping how the x and y axes interact, what a steep slope actually represents, and that crucial fact that a horizontal line means a full stop, we completely decoded what looked like an abstract image. We took a basic grid and a few scattered data points, and we turned them into a dynamic, unfolding story of a race, complete with variable pacing, rest stops, and a perfectly calculated come-from-behind victory.
I really hope this breakdown made reading distance time graphs crystal clear for you. If you found this explainer helpful and you want to keep mastering math through clear, structured, and visual lessons just like this one, please make sure to hit like, share this with a friend, and smash that subscribe button. We've got plenty more stories hidden in the numbers just waiting for us to decode together. Keep learning, stay curious, and honestly ask yourself, the next time you're on a long road trip, what would your graph look like? I'll see you in the next explainer.